Okay, folks. Well, a lot of you missed a very big event on Saturday, but a bunch of you came. The Moonlighters Jazz Band had a big crowd last Saturday night, and there were 6 or 7 or 8 of you in this class who were there. And that included Jonathan. Where are you, Jonathan? Are you here? And it was Zachary. Where's Zach? Zachary. It was Parneet. Parneet, where are you? There you are. Are you all sitting together? Is that right? Taylor. Hey, you're all together. Eric, is he here? No, he's not even in the class. And Yuyen, there you go. Did I miss anybody? Who did I miss? Oh, Christian. Kristen, yeah, right, Kristen. And in fact, Jonathan had the highlight of his life because we have a very attractive vocalist who was all dressed up, and she sat on his lap during a main number here. So, you know, it was, how about that? You know? So, right? And you have fun? I thought you had fun. Okay. So, next time we play, I'll let you know. I'm not sure when that's going to be, but, you know, we were pretty good. So you ought to consider it and ask them whether we were good or not. This is a professional band. So, anyhow. So, by way of introduction, the Moonlighters Jazz Band. Now we're going to talk about modeling strategy guidelines. And I want to continue from where we were, but just to review quickly, these are guidelines, so these are not rules. There are a couple of rules in there, but they're mostly guidelines so that for allowing you to figure out how to come up with the best mathematical model when you're using logistic regression, or actually any other kind of regression modeling procedure. It carries over to survival analysis, Poisson regression, linear regression. But we're describing it in the context of logistic regression now, and it's a 3-stage strategy, and the goal of the strategy is to come up with a valid estimate and decision about to what extent there's a relationship between an exposure, it could be more than one exposure, and a health outcome variable. So that's the goal of the strategy. We've seen these pictures before. And there's 3 stages. I'm trying to kind of walk through what I said last time, and these are listed in the order in which you should probably do them, and the order in which I'm recommending that you do them. Variable specification, followed by interaction assessment, provided that you are interested in interaction, and then followed by confounding, and followed by the third step is confounding, followed by precision. Confounding should sort of take precedence over precision because if you have you want to make sure you get the right answer before, rather than get a tight confidence interval around the wrong answer. That's why confounding is preferable to precision, and interaction is preferable to the second step is preferable to the third step, in the sense that if you find strong interaction so that the effect is different, for example, for males, the odds ratio is different for males than for females, you don't want to come up with a summary estimate that averages over the 2 genders, because you're missing something. You'd be sort of masking the real underlying message that the relationship's different depending upon whether you're male or female. And variable specification comes first. Why? Why did variable specification come first? I talked about that a little bit. It comes first because that's where you want to make sure the variables that you're considering are something that's related to what's really going on, that they have something you can draw conclusions of, that makes sense, corresponds to the literature or whatever the conceptualizations of what you're doing. So these are the 3 stages. And I started talking about the three stages, and I did all this here. And I said something about confounding, and we'll go into that more today, that the assessment of confounding shouldn't involve statistical testing, because why is that? Because confounding is a validity issue. It has to do with systematic error as opposed to random error. You don't test for confounding, and you learned that when you took 530 and 534, and it carries over to even when you're doing regression modeling. So you don't evaluate confounding by doing a statistical test. You have to do something else. You have to decide about whether an odds ratio or whatever your measure of effect changes meaningfully as opposed to using a statistical test. And I did mention that there were these other issues that we're going to talk a little bit more, well, somewhat more about collinearity or multicollinearity, and I've said a little bit of something about each one of these issues, multiple testing and influential observations, which have to also be considered, even though at this point right now we're not going to go into any of these things any more than I already mentioned up to this point. And so then I spent some time talking about the variable specification stage, which is the situation where you're starting with a health outcome, the D variable. You've got an exposure variable. You may have more than one exposure variable, but for now I'm only going to consider one exposure variable, and more or less we're going to consider it as a binary variable, although it could be continuous, because you've also learned when Eli was reviewing with you how to get odds ratios. You can also talk about getting an odds ratio for an exposure variable when the variable is continuous, whether it doesn't have to be binary. But for the most part, we're going to focus on, think about things binary for now. And then there's the D variable, the E variable, and then there's the variables that you want to control for, called the C variable. You want to consider for control, called the C variables. And these may either be confounders or effect modifiers, and they're going to go into the model to reflect those things, confounding and effect modification. And the kind of model we're going to be considering that allows for variables in the model that are more complicated than just the C's themselves is called what? What's it called? What's that more general model called? The EVW model, because it's going to allow for not only might just put only the C's in there, but you might put functions of the C's. If one of the C's is age, you might have age square in the model. If one of the C's, in addition to age, is race, you might have age times race in the model. And if you do, that's a V variable as long as it's not in there as a product term with E. If it's in there as if age times race is in the model as a product term with E, then age times race, in addition to being a V variable, is also a W variable. Okay, you got that? I'm not sure, but and so the variable specification stage, what I said last time is specify the V's basically from common sense, from prior researcher history, or from the literature essentially, and don't get too complicated with the V's, because if you put variables like age times race times smoking times body size as V variables in the model, you might be asking for all sorts of statistical problems like collinearity. The model may not run. And even if the model does run, you might not be able to figure out what it means if you had a four-way product like that actually coming out in the model as staying in the model. So these are the things that you have to consider when you specify the V's. And of course, the simplest choice for the V's are just the C's, but you might want to consider a V that's more complicated. If age is one of the variables you want to consider controlling for, you might decide to also put in age square. I mean, if it makes sense based on the literature or where age square comes in, the relationship between age and the outcome might not simply be linear. It might be in some kind of a nonlinear way or quadratic way. So I talked about the V's, and then I talked about the W's, and I made a recommendation that the W's shouldn't be probably either the V's, they should be probably no more complicated than either the V's or two-way products, two-factor products among the V's, but not necessarily any more complicated, even though there's no restriction which says, no formal thing that says you can't have anything. I mean, you can put whatever you want in the model. It may turn out if you put in the model E times age times race times sex times body size, that kind of a variable in the model, well, it may turn out that maybe it does make sense, but not likely, and it's probably going to cause you more trouble than it's worth. So that's why I'm saying it makes more sense to not go any more complicated than E, VI, VJ variables, or just simply EV variables, to keep the model simple, interpretable, and reasonable to be able to analyze. So that's what we talked about. And then I got to the point, I said, well, we're really dealing with a flow diagram. We're starting with the D, E, and the C's. We're choosing the V's from the C's, and then we're choosing the W's from the C's as either VI or VI times VJ, and the W's go in the model as product terms with exposure. And that's your initial model, okay? And now, then the one other key point about the initial model that I talked about was the model has to be what's called hierarchically well formulated, HWF. And that means that what I say here, it's a simple idea, is that given any variable in the initial model, all lower order components of the variable must also be included in the model. That's what the key thing that you have to make sure you maintain in your model. So if you consider this model, this was an example I showed you, if you consider this model is not hierarchically well formulated because the largest term in the model, the largest highest order term in the model, there's a lower order component, V1 times V2, which is not in this model. So this isn't hierarchically well formulated. And then I talked about, well, why do you have to have it hierarchically well formulated? You remember that? And I gave you an example. This is almost where we were. I gave you this example. And I basically said, here is an example where it looks like there's interaction between the interaction in these two groups. The V1 variable is, and it looks like an effect modifier because the odds ratio is 36 here and it's 1 over here. And then I gave you we pointed out two choices of different models, one of which was hierarchically well formulated and one of which wasn't. The second model is not hierarchically well formulated because any of the lower order terms of E times V1 is not in the model. And so if we looked at, so what I'm saying, it would be incorrect to use the second model, it would be correct to use the first model. And the reason why was that if you fit both these models and you tested for the highest order term in the model, then it would turn out that no matter how the variables in that highest order term were coded, there's either the E variable as either 0 or 1 or -1 1 or 1 2, that highest order term is going to give you exactly the same test statistic value, regardless of how you've coded it. However, if you're using a non-hierarchically well formulated model and you try to test for the highest order term, you can get different answers. Meaning that you can't rely on a model like this that's not hierarchically well formulated to test and make a decision about what the significance of the highest order term in the model. So that's what I sort of said in the previous slide here. Why require HWF modeling is because if this model is not hierarchically well formulated, then the test for the highest order variables will depend on the coding. Whereas if it is HWF, then the test for the highest order variable will be independent of the coding. Now you may notice, for example, that in this example, you notice that even in the model that was hierarchically well formulated, look at the test statistics, the wall tests. Really you want to do likelihood ratio, but the wall test statistics for these lower order terms like E and V, they're not the same, right? The 32.44, it's the same for all three coding. But these numbers, like this 0 and this is 32 and this is 12, they're not the same. So what's that all about? Can that happen? Well, yeah, it can happen. But you see, if you have a model that has this product term and these lower order terms, you don't want to test for these lower order terms until you've made a decision about the highest order term. So you're really not interested in these tests, even though they could be different. But if it turned out you found out that that's not the case here, but if you found out that this highest order term was not significant, then you could drop it and then look at the highest order term in the reduced model. But at this point, you're not interested in these lower order tests. You get what I'm saying? I'm not sure if you're getting what I'm saying here. But so again, the message is you need a hierarchically well-formulated model. That's the message. And that's sort of where we ended last time, other than to say we're going through an approach that starts with an initial model. That's the largest model we want to consider, not necessarily the largest model possible, but the largest model we consider reasonable to consider. And then we're eventually going to work our way back from this largest model to a smaller model that's going to allow us to consider interaction and allow us to consider confounding. Now you notice I said testing, testing, and I said no testing here. Why is it testing, testing? I talked about this the last time. Why do I have testing, testing for these two things, but I don't have testing for here? Because these two things have to do with interaction. You can test for interaction, but you can't test for confounding. And the reason why is confounding is an issue that has to do with systematic error, but that's not what interaction is. Interaction doesn't deal with systematic error. It deals with understanding the relationships involved, the causal relationships. You can test for interaction. And that's a well-established, well-understood or accepted idea in the epidemiologic methods literature, that you can test for interaction, you can't test for confounding. Okay, so now we're going to look at an example, but before we do, there's one more thing I want to add to this, which is, again, something new. I want to talk about something called the hierarchy principle for retaining variable. But this is a new slide, right? You didn't. It might have had it popped up there last time. This is a new slide. And what does this say? It says it gives you. It's another principle that you have to sort of take into account. And it has to do with the process of what you're going through after you've defined your initial model and you're starting to go through the process of figuring out what the best model is. And what it says is, if a product variable is to be retained, then all lower order components of this variable must also be retained. Now, this statement looks like it's saying the same thing as hierarchically well formulated, but it's not. It has to do with the process. And think about it this way. Think about this. Suppose you have a model, as I have illustrated here, which actually has terms like this: E times the product of two V's. You have those terms. You also have EV terms. You have V terms, and you have E in the model. So think of a model that has terms at least as high as E, V, I, V, J. And suppose it turns out that when you assess interaction, remember after the initial specification of the model, what's the next thing you do if there's interaction terms? You assess interaction. That's the next thing you do. Okay, that's the second stage. The third stage is confounding, follow, and we haven't gone through the specifics of how you do this, but suppose it turns out when you start to assess interaction, you find that this term, EV2, V5, V2 is the second of the V variables, and V5 is the fifth of the V variables. You suppose you find that when you start looking at interaction, you find this three-way product term to be significant. Now, what this principle says, what this statement says essentially is, once you've decided that this is significant, meaning that you got to keep that variable in the model because it's significant. You've allowed yourself to have a model with this three-way product term and maybe some others, but suppose this one is significant, maybe the others aren't. And this is the only one that's significant. Well, this rule says if this is significant, in all further aspects of what you're going to do to come up with your best model, you have to keep all lower order components of this in your model. You can't drop any of those. Well, what's lower order components of E, V2, V5? Well, one of them is V2 times V5. That better be in the model. If it wasn't in the model wouldn't be hierarchically well formulated, right? So you have to have V2, V5. Now, this says if you find this significant, and you started off with a model that had E, V2, V5, and better have V2 times V5 in the model, this rule says you can't even ever consider dropping V2 times V5, because you already have a term in the model that's including that with exposure, as a product with exposure. So you can't drop V2 times V5, and you can't drop any lower order terms, any other lower order terms, one of which is E, one of which is V2, one of which is V5, EV2, EV5. You can't drop any of those terms. So this says as you go through the process of trying to come up with the best model, once you decide a certain term has to stay in, then you have to leave all the other lower order components in the model. That's what it says. Now, why? Well, I mean, what if, the argument, the counter-argument was, well, maybe I can still drop V2 times V5 from the model, even though I'm keeping E2 times V2, V5 in the model. Why can't I drop V2 times V5, even allow myself to drop it from a model that has E, V2, V5? Why can't I do that? I don't hear anybody. Well, the Moonlighters have to come on and entertain you here? Why can't I drop V2, V5? Because if I drop it from the model, if I decide it's not significant or I decide I don't need it for some reason, then I have a model that's no longer hierarchically well formulated. I have E, V2, V5 in the model, but I wouldn't have a lower order component of it. So I can't drop any lower order components for whatever reasons, because then the model is not hierarchically well formulated. So that's what this says. Now, suppose it turns out that E, V2, V5 is the only three-way product that's significant, okay? And so in other words, E times V1 times V4 is not significant, okay? Well, does that mean maybe I can drop, that means I can drop E1 times what did I say? E, V1, V4. I can drop that if it's not significant. Can I then drop V1 times V4? Am I allowed to drop V1 times V4 if it's not significant or not a confounder? And the answer is yes, because it's not already contained in a higher order term. So I can allow lower order terms to be dropped if they're not part of higher order terms that have to stay in the model. That's what this says, okay? And you have to kind of use this as you're working through your modeling strategy to come up with the best model. And right now, I mean, we've got all these practice examples and stuff like that we're going to work through so that you can understand this better. But that's what this rule says. So now what we're going to do is we're going to now look at the MRSA example and walk through how you would assess what the best model is here using this example that you've seen now a whole bunch of times. You saw it not only in this course, you saw it in 534. So in this example, the outcome variable is a binary variable, whether or not somebody has MRSA, yes or no. The main exposure variable of interest is whether somebody had been previously hospitalized, and there are 3 C variables to be on the list for control variables: age, gender, and previous antimicrobial drug use, denoted here as PAMU. Okay, and so that's your set of variables. And now the first thing you have to do in the modeling strategy is to come up with a with your initial model, which is the variable specification stage. And we're going to, because we want to consider confounding, interaction, and possibly precision, the model is going to be an EVW model. We just have to decide what the V's are going to be and what the W's are going to be, given this is our situation. And of course, the simplest thing we could do is say, well, let's make the V's just the C's themselves, and let's make the W's just the C's themselves. Isn't that one decision? Just make the V's the C's, and just keep the C's as the V's and the W's. That's the simplest thing. Why is it simple? It's simple and nice because it allows us to consider confounding for all 3 C variables, and also allows us to consider effect modification for all 3 C variables, and doesn't get us into something more complicated by putting in a product term, age times gender, or age square. By the way, gender square, can we put in gender square? This is sort of a joke. Can you put in gender square? Ha ha ha. What's gender square? Gender, right? So you can't square a variable that's a 0, 1 variable, so you can't do that. But you can put an age square, age cubed, you can put age square times gender. You know, you can have the EVW model be much more complicated. The simplest thing is just keep the C's, the V's and the W's to be the C's. And in order to actually work through an example, that's what I'm going to do. To do that, even though anybody, in particularly whatever they're doing, whatever their research, could decide whatever they think is more meaningful to do and not do this. They could choose something other than just the C's themselves to be the V's and the W's. But that's what I'm going to do here. So on my next slide, I say, let's just make the V's and the W's the C's. So this is our initial model. There's the E variable, previous hospitalization. There are 3 V variables, the same 3 variables as the C variables. And there's 3 W variables, which are also the C's. So that's our model. Okay? That's our initial model. So here in the corner of the screen, I say, is it hierarchically well formulated? Got to make sure it is. Is it? Is every lower order component of this model contained in the model? And if you look at it, well, this is EW3, and W3 is just C3, and E is in the model, and the lower, since W3 is C3, and C3 and V3 are the same variables, all lower order components are in this model. Even though the terms that I'm using to denote them are slightly different, but the V's and the W's are just the C's themselves. So this model is hierarchically well formulated. So I can start with this. I don't have to worry about adding something to the model to make it legitimate. This model is a so-called legitimate model. Okay? You with me? Questions? Okay, so hierarchical formula, there's a check. We've done the variable specification. Next question is interaction assessment. Okay, so now we're talking about the interaction assessment. What do we do here? Well, we want to focus on these 3 terms, right? These 3 terms, the 3 product terms, because those are the interaction terms. Well, how do we do that? Well, there's a number of ways to do that, okay? What most people would usually do is to do what's called, and I think Eli might have referred to it, but I think I've already referred to it, do a chunk test for interaction. What's a chunk test for interaction? What would be the null hypothesis in terms of this model and the parameters in this model if you wanted to do a chunk test for interaction? What would be the null hypothesis? Delta 1 equal delta 2 equal delta 3 equals 0. All 3 deltas is 0. How do you do that test? Likelihood ratio test, right? You fit 2 models. The full model is this model. What's the reduced model? Doesn't have those 3 product terms. You know how to do that. You would just have to run 2 models if you were using proclogistic and look at the 2 minus 2 log L values that you get on the output and subtract one from the other, and it would have how many degrees of freedom? 3. So this is a piece of cake to do this, right? So let's say you do this, okay? Now, let's talk about, now it turns out when you do this for these data, it turns out to be not significant. It's not significant. But let's just pretend that you did this and it was significant. Let's just think about it. Suppose you did this chunk test and it was significant. What does that mean? What would you do at that point? Chunk test is significant for all 3. Well, you got some options. I mean, one option would be, well, I'll just keep all 3 in. You know, I'll stop right there. I've got my final model. I'm going to put all 3 in because I need those 3 terms. Well, there's another way to think about it. It may turn out that maybe, even though the chunk test was significant, maybe it's significant primarily due to some subset of these 3 variables, not all 3 variables. So maybe I don't need all these 3 variables, okay? Maybe I can drop some of them because some of them aren't doing much, and there's really 1 or 2 others that are really, 1 or 2 of them are really doing most of the damage, you might say, to make it significant, okay? So how do you deal with that? You do something called, if you're starting with a model that's got everything in it and you want to drop some variables, what's the approach? Go backward elimination, right? That's what you do. You do backward elimination. How do you do backward elimination? Well, we'll do it here. You drop the least significant one, reduce the model, drop the next least significant one. You keep doing that until you can't drop anymore, or until you can't proceed anymore. Okay, that's what you do. And the model that you wind up with is the model you get after interaction. So let's now, before I continue, it turns out that that's what you would do if it was significant, but it wasn't. It wasn't significant. So what do you do if it's not significant? The chunk test is not significant. What are you tempted to do? You're tempted to drop everything. Drop, not everything, just the product terms, right? Because all you're testing is the product terms. Well, is there a problem with that? Is there a problem with that? Is there a potential problem with that? Well, you could say, taken together, they're not significant. I don't need any of them. Well, it may turn out that the reason why the chunk test was not significant was because I put three variables together, some of which, two of which, or some of which cancel each other out in terms of their ability to predict the outcome or describe the relationship or describe the interaction. So maybe it turns out that even though when I put all three variables, three product terms in the model, it's not significant, maybe it turns out that if I drop one or drop two of them, one of them or two of them might be significant anyhow. It's just that I didn't need that. If I try to put all three in, I didn't get anything significant. So what would that suggest you do? Even if the chunk test is not, this is something that you usually somebody asks a question about this when I get to this, but what is this, based on what I just described, what does it suggest that you should do, even if the chunk test is not significant? You still do backward elimination. Either way, okay? So whether it's significant or not significant, you still do backward elimination. So what's the question that some of you will ask? Why? Sorry, I just got carried away. Why do the chunk test at all if you're going to do backward elimination? I just get silly, So why do the chunk test at all if you can do backward elimination? Well, there's a reason. We'll explain. We'll talk about this as we get through it. But let's look at the example here. So what I'm saying here is saying carry out the chunk test, and depending on whether it's significant or not, if it's not significant, you could eliminate all the terms in the chunk. That's one approach, and or use backward elimination, which is what I'm saying you should do. If it's significant, you might retain some terms by using backward elimination to eliminate some others. That's what I'm saying in this flow diagram about interaction. But let's actually look at this. Here's the model that we're dealing with. Okay, it's got age, gender, PAMU. These are the three C's. It's got the three C's also as W's. And the question is, how do you test whether there's no significant interaction of any kind in the above model? We've already answered that. Chunk test. If the above test is significant, what would you do next? My answer is backward elimination. If the above test is not significant, what would you do next? My answer to that is you would also do backward elimination. Now it sounds like, well, why do the chunk test? So let's get at that, okay? Now it turns out, here's what happens when you do the test. I'll show you the results. When you do the test, well, remember the null hypothesis is that all three deltas are equal to 0. It's a chi-square with 3 degrees of freedom. And when you fit the full and the reduced model, you get these two log likelihood statistics, which you subtract. And when you subtract them, you get 2.096 is the chi-square statistic with 3 degrees of freedom. When you go to chi-square tables, you find it's not significant. So the chunk test is not significant. So now we know it's not significant, so we're not, I said if the above test is significant, well, we know we're in this stage now. It's not significant, okay? So let's go through the process, okay? I'm doing backward elimination now, okay? And I'm going to do it using the wall test to make the decisions. What's the problem with that, doing it that way? Using a wall test to make a decision about whether something's significant instead of what? The likelihood ratio test. What's the problem with doing a wall test? What about walled versus likelihood ratio? What about those two tests? What have we said about them? We said that one of them's better, right? And why did we say they were better? Well, I said it, Eli said it, ask anybody in the biostatistics department, they'll say it's better. Why is it better? Well, this is where you have to trust the statistician to say it's got better statistical properties. That's why it's better, okay? And what that means is that it's possible that if you do the wall test and the likelihood ratio test, you might not get the same answer for the two tests. You might not get the same answer for the two tests. Even though usually you get something that's very close, but you might not get the same answer. And if you get a different answer, and one of them says reject and the other one says don't reject, which test are you going to use? Likelihood ratio, why? Because statisticians say it's better. That's why you're going to use it, okay? If you use, okay, so by doing the wall test here, I'm taking a chance. Okay, but let's now go through this. Now, here's the model that we started off with. It has everything in it. It's got the E variable, it's got the three C variables, it's got these three product terms, E times C. They're called PRH is previous hospitalization times age, previous hospitalization times gender, previous hospitalization times PAMU. And here's the output just for this model. And it's got the degrees of freedom, the estimate, the standard error, the walled chi-square. How do you get the walled chi-square? The estimate divided by its standard deviation squared. That's how you get the walled chi-square, okay? So the 1.7474 is this 1.1693 divided by 0.8845 squared, okay? Now, in the right-hand column is the p-value for the wall test. The computer automatically gives it to you. Now, these p-values, by the way, are they one-tailed or two-tailed? Did anybody say anything about that? I think I said it last semester, but I don't know if Eli did. The p-values that you're getting that the computer prints out are all two-tailed. They're all two-tailed. If you want to do a one-tailed test, what do you have to do with the p-value to make it a one-tailed test? You have to halve it. You have to half the p-value. If you're testing for interaction, typically you usually do two-tailed tests because you don't really know which side, in advance, which side you're interested in and whether there's interaction or not. You could, but usually you don't. Now, I go down this list here and you notice this number is in bold, 0.6010. Why is it in bold? Why is it the only one in bold? Because it's the p-value that's the highest p-value. That means what? It's the least significant, right? It's the least significant among what? Well, is it the least significant among all of these p-values? Well, there's one that's 0.97. So this is the least significant among what? The three product terms that we're testing. Those are the ones we're looking at. Okay, so when you do backward elimination, what you do is you say, which one is the least significant? And if it's not significant, I drop it and I go on to the next model. Okay, so when I do that, that means I drop previous hospitalization times age, and I'm left with these other two variables. Okay, now by the way, one thing that's wrong to do when you're doing backward elimination, you notice that all three of these p-values, all three of them are not significant, right? They're all above 0.10. They're really high as far as significance is concerned. What is there a temptation to do because all three of them are not significant? Drop all three, okay? But if you do that, that's wrong. That's not equivalent to doing the chunk test. The chunk test tests all three at the same time. Each one of these tests one given the others in the model. So it wouldn't be appropriate to look at the three p-values and say they're all not significant and then drop all three. You got to do it one step at a time. Okay, you may have to think about that. Okay, so now we go to the next step. Now you notice the highest p-value. Now it's among these two is this one, so I drop that. Okay, and so I'm left with this one. And the only one I have, and the p-value here is not significant also, right? So what does that say I should do about these three product terms? Using backward elimination. I can drop all three, because when I do it one step at a time, I can drop all three. Okay, so it turns out that the answer that I got from the chunk test as far as this going backwards, is exactly the same as the answers I got if I did backwards, right? The chunk test says not significant, backward elimination says not significant. So I got the same answer. Will that always happen? Not necessarily. It happens here, okay? Now, for example, just to give you an example, what if it turned out when we got to this point, instead of 0.2122, this was 0.021, 0.0212. In other words, I dropped the first two. When I got to this one, it was significant, right? What would I then do? Would I go with the chunk test, or would I go with the backward elimination? And what would the backward elimination say? I can't drop this one, keep this one. Okay, so now it looks like I got different answers from the chunk test and backward elimination, and I'm going with the backward elimination one. So I'm still still haven't answered this question, why I still want to do the chunk test. Okay, because it looks like I'm still doing backward elimination. Okay, anybody got any ideas? Well, let me give you an idea. Okay, suppose instead of 0.2122, okay, suppose this was 0.0490. 0.0490 instead of 0.2122. That's significant? Well, it's significant at the 5% level if you're talking about a two-tailed test. Is it highly significant? Barely significant, just barely makes it in terms of the 5% level, right? It certainly isn't significant at the 1% level, right? It's not strongly significant, as it would have been if you got 0.02 or 0.002 for this thing. So if it turns out, when you get to this third step, when you do this backward elimination, and it turns out if the answer that you get is significant or borderline significant, maybe it was not 0.0499, maybe it was 0.0602 or something, barely over, just barely over 0.05. Okay. Now, in that case, you might say, well, look, I did the chunk test. It was not significant. When I go backwards, it looks like there's one of these that's barely significant, but not strongly significant. That's a situation when you might go with a chunk test, because you don't have a variable that's really standing out of those three variables, even though one of them looks like it's almost there. So it's a judgment call. There are a lot of judgment calls in here. Andrew, got a question? Or you question? You're talking to your friend over there, but what about your friend Mark? Yeah. And Mark is talking. No, it's okay. Okay.
We've done backwards elimination then.
Well, what I'm saying is, it's not superfluous, because once you got to this point, you got something that was significant. It was borderline significant. Okay. Now, the chunk test said when I took everything together, I didn't get anything significant, taking it all together. So I might say, look, I want to weigh these two bits of information together, and maybe I'll go with the chunk test. That's why I'm saying maybe you could still do the chunk test even if the chunk test is not significant. I don't know if I'm making that point clear. So it's not automatic that you just do backward elimination and ignore the chunk test. I mean, you could get, if you get different answers, and they're not borderline, like I gave when I said was 0.02, then you definitely go with backward elimination. But if you're getting almost the same answer, not exactly, but almost the same as you get with the chunk test, maybe it's not worth putting in assuming some interaction that's not hardly there. The more interaction terms you have in your model, the more difficult it is to interpret everything and all of that. So that's a reason why I'm saying that. Okay? I don't know if so that's that. Okay, so at this point in our process, this is our model at this point. You see this model? That's our model at this point after the interaction assessment. Correct? There's no product terms in the model. Okay? We've gotten rid of these product terms because of the likelihood ratio test and backward elimination and all of that. It makes sense because of what we got. So what's the next step? Confounding and precision. And of the two, confounding is one you first should do. So what do you mean by confounding in this case? Let's just, we're trying to review this. What do you mean by confounded? I have to keep thinking that, okay. So how do we deal with confounding? Well, what we're asking is, we know E has to be in there. That's our exposure variable. So we're asking, can we drop either one or more of these other three variables because they're not confounders? Can we drop them? Can we reduce the model by getting rid of some variables that aren't dealing with confounding? And then we also want to consider at some point precision. Maybe if we have a variable that's not a confounder, maybe it still is doing something about precision. So maybe we still can't automatically drop it. So how do we do that? Okay, well, here's the idea. We're not going to test for confounding. The first thing you might think about doing is, why don't we start with this model and start doing a backward significant testing with age, gender, and PAMU and see which one we can drop. Keep E in the model and drop the least significant one among age, gender, and PAMU. What's wrong with that? What's wrong with doing significance testing going backward? What's technically wrong with that? Confounding, you don't do a test for confounding. That's what's wrong with it, right? There's got to be some other way. Now, there is a variation on this that we'll still talk about if I have time today, but anyhow. So what you're going to do is you're going to say, you're not going to do a test, you're going to see something about whether there's a change in the estimate. Change in the estimate. Whether there's a meaningful change in the estimate. Now, here's the model, and here's the full model at this point where there's no product terms in the model. It's got these E and the 3 C's. It's like rock and roll band, E and the 3 C's, right? Okay, so here's the fitted model, okay? Okay, now you notice that for this fitted model, I put the number for previous hospitalization, 1.4855, that's in bold. Why is it in bold? Because that's the coefficient of the exposure variable. So what's the odds ratio for this model? The exposure variable is 0, 1. It's E to this coefficient, right? E to the beta. You know that. You knew that. Even before you came into the class. Okay? E to the beta. When I take E to the beta, it's 4.417. That's what it is. That's the odds ratio for this model. Now, this model I often refer to, and I haven't done it on this slide, as the gold standard model. This is the model after you've assessed interaction that's controlled for everything. And what you want to do is you want to see if you can drop something. Maybe you can get away with not controlling for all these, but with this model, you've got everything in there that you were worried about. So in some sense, it's the gold standard model. That's the odds ratio, 4.417 in this gold for the effective exposure, and that's its confidence interval. Pretty wide. It's wide, but that's the. So now, suppose I start saying, well, can I drop one or more of these variables? One or more of either C1, C2, I can't drop E. Now, let me ask you this. Suppose I dropped one of these. Suppose I dropped C3. Got rid of that from the model. And I fit the model that has E, C1, and C2, but doesn't have C3. What's the formula for the odds ratio? For that model, for the odds ratio for the effective exposure in that model. Doesn't have C3. What's the formula? It's E to the beta, right? It's E to the coefficient of the exposure variable. Is E to the coefficient of the exposure variable in the model that doesn't have C3 going to be the same as E to the beta in the model that does have C3? Well, I don't know. I have to see. That's what you'd have to do. You'd have to see. And if it's very different, then I can't drop C3. If it's almost the same, then I can drop C3 and the odds ratio doesn't change. So I don't need C3 to get the right answer. I can drop it and still get the same answer as when C3 is in there. So C3 is not a confounder in that sense. So let's look. Let's look. Now here's a model where, now you notice it's got gender and PAMU. I've dropped something. What have I dropped? There it is. I dropped age. I fit this model. This is what I get. For this model, these are the coefficients. And you notice the coefficient is 1.6627. It's not 1.4855. It changed. Okay. Then I go E to the beta for this model, and I get 5.274. Right? That's what I got. Okay. And for the previous model, for the gold standard model, I got 4.417, right? 4.4 for the gold standard model and 5. Now, is that different? Are those two numbers different? Well, I'm not going to decide they're different from a statistical test because I can't do that. So how am I going to make a decision? You do this thing, like, is it meaningfully significant? You have to make a decision. Is what do you mean by meaningfully significant? And you learned something when originally you learned about confounding, is that there's different kinds of rules, and a very popular rule, it's a guideline, is the 10% rule. Now, you don't have to use it. You could use a 15% rule, a 20% rule. But you could ask if you decide you're going to use a 10% rule, what you're asking is the 5.274 more than 10% different from the 4.417? That's what you're asking. Get what I'm saying? More than 10% different. How do you figure that out? Well, you take 4.417, you take 10% of that, which is 0.442, and you add and subtract the 4.417, 0.442, and this is the range you get. Okay? Now you look at this number. Is that in that range? No. So that 5.274 is not within 10% of the gold standard odds ratio. Okay? Well, that means it's not within 10%. That means I better not drop it. Because if it was in 10%, maybe I could say it's not a confounder. I get the same answer. But it's not the same answer. It's different. Okay? So, you know, what you notice that I've got an X over here for this model. Why do I have the X? Well, for this odds ratio. Because I can't drop age in order to get the right answer, as the same answer as the gold standard. Well, look at the next one. What have I done in the next one? I've dropped gender. When I drop gender and I look at what I get 1.4679. I go e to the beta, I get 0.4340. Is that in here? Show enough, as they say. Yeah, it's in there, right? So what does that mean? I can drop gender and still say I'm controlling for confounding. Okay? So I'm legitimately can drop gender. It's not necessarily a confounder as far as being within 10% of the gold standard. Okay, so am I finished? No, because there are a whole bunch of other things I could do. Now, what did I do here? I dropped PAMU. What happened? No, right? Can't do this. What did I do here? I dropped two of them. I dropped gender and age, right? What happens? Well, 5.136 isn't bad, but it's not in here. So if I'm using the 10% rule, I can't drop I can't drop PAMU, and I can't drop these two variables that were dropped here. And then if I keep going that way with, in this case, I'm dropping, what am I dropping? Gender and PAMU, and here I'm dropping age and PAMU. And you notice there are X's here, meaning that if I keep doing this, I can't drop any of these other variables. I'm talking about dropping either one at a time, two at a time, and if I drop all three at a time, what am I talking about? Dropping all three at a time. If I drop all three at a time, what model do I have? I just have the crude data, right? I'm not even controlling for anything. I have to examine that too. Well, now look at what I do here. Look at this table. This is sort of the summary of what I've just done. At least the first two columns are the summary of what I've just done. And what I've done is something called the all possible subsets approach to coming up with assessing confounding, the all possible subsets. I'm considering, okay, I have three variables. Okay, I'm considering dropping them one at a time, two at a time, or all three at a time. I'm allowing myself to consider every possibility, okay, which is the safest way to do this thing. It's in a way the best approach, okay. Now look at what happens when I go down this list. These are all the odds ratios I showed you when I did all this. They're all now in this second column, okay. And there's only one odds ratio other than the gold standard that's in bold. Why is that? Because that's the only one where, see the third column says within 10% of the gold standard? This was the only one that was within 10% of the gold standard. If I'm going to use the 10% rule, this is the only other model. I can only drop gender. I can't drop anything else. That's what this says. Okay. So where am I at this point? What I've done is I've gotten to the point where I started with a model that had all three of these in here. And then I've said, well, if I want to make sure I control for confounding using a 10% rule, I can get away with dropping gender, but I can't drop anything else. That's what it says. So I now have gone from as many different possibilities, all these different other models, to just two models, the gold standard and this model. Okay? These are the two models that give me the same answer. The right answer is the gold standard one, because that controls for everything. I don't know if that makes sense to you, but that's the idea here. The right answer is the gold standard one. Follow me? Okay. So now, what's next? Well, I've just dealt with confounding. You remember there's variable specification, interaction, confounding, followed by precision. So when we talk about precision, we're talking about confidence intervals. Okay? So let's talk about confidence intervals. Okay? So here are the confidence intervals for the odds ratio for each one of these models. Each one of the models that were all possible subsets. But you notice I only have two sets of confidence intervals that I've got in bold. Why is that? Because there's only one competitor to the gold standard model, this one. I don't care about these other confidence intervals because I don't want to get a confidence interval around the wrong odds ratio. So this is the only other confidence interval I want to consider to compare it to the gold standard confidence interval. Okay, so that's the confidence interval. Now, when you talk about precision and you're looking at a confidence interval, there's two ways you can look at it. And you may have heard this before. I'm not sure if I said this when I was talking about logistic regression 534. One way is to say, well, how wide is the confidence interval? When you talk about how wide the confidence interval, what do you mean? The difference between the highest and the lowest. 7.730. The difference between the highest and lowest here, 8.892. The difference between the highest and lowest, 7.470. Okay, so this column is the width, difference between the highest and the lowest. Okay, now, the smaller the number, the better the precision or the worse precision? The smaller the difference, the better? Yeah, the better. So, of these two models, which gives better precision? According to the width. The one that drops gender, right? It's smaller. It's a little smaller. Okay? Now, what's this column? It says CI ratio. Well, this is something we've got to talk about here a little bit because, see, when the measure of effect is a ratio estimate, and you're talking about an odds ratio, problem is that, and you're talking about a confidence interval, it could be that and you're talking about the difference could be affected by what the initial value is. You divide the highest by the lowest, and if the lowest is real high, the difference might not be that the difference might not be that high because the lowest was high to start with. Couldn't go up that much. Okay. So what people tend to now recommend is that instead of using the width, using the ratio. So what do I mean by the CI ratio? What's 4.857? How do you do that? 9.734 divided by 2.004. You divide the highest by the lowest rather than subtract the lowest from the highest. And when you do that, I get something that's sort of not dependent on the first value, the lowest value. And when I do that, what do I get here? I still have these two numbers in bold because they're the only two things I'm comparing. Okay. And what happens? Do I gain precision or not? If I drop gender, do I gain precision? Yeah. So either way, whichever one I do, it looks like if I drop gender, I get the right answer and I gain precision. So which model's better based on that? The one that drops gender or the gold standard model? Well, it looks like the drop gender model is better because it gives you the same answer and it gives you a little better precision. Okay? Now, there's a counter-argument to this, which says the following. It says, well, it starts dealing with sort of a little bit more realism here. Now, it's true that this precision using either one, but this precision is smaller than that. Is it a lot smaller? Well, how much smaller is a lot smaller? That's what you start getting into. How much smaller is a lot smaller? You know, which again is a judgment call, okay? But what a lot of people do in this case is what they do is after they say, well, look, I think this model's better because it controls for confounding and gives me better precision. However, if I've decided that if it controls for confounding, but I don't gain that much precision by dropping it, maybe I better use the gold standard model because then everybody could see I controlled for everything and I didn't really gain much I didn't get that much precision. I didn't get very much of a tighter confidence interval by dropping it. So there's a counter argument. The counter argument in this case is to say, let's go with the gold standard because you didn't gain much precision. Now, you have to make a judgment call about whether going from 4.857 to 4.752 is a lot. And that's debatable. You may decide is it 10% or something like that. I don't know whether there's a 10% rule on this. I mean, I don't know about any kind of a rule. So what I'm saying is, the process, what this table does, it describes a process. It says, look at all possible subsets. Okay. Then decide on confounding by looking at the odds ratios for all possible subsets, comparing it with the gold standard odds ratio, and then saying, okay, I'm now going to get rid of some of the models. And I'm only going to, in this case, I only have one other competing model. Then I'm going to look at the confidence intervals around the competing models. There's only one competing model. And I'm going to see if I gain precision by looking at some of these other competing models. If I gain what I think is a lot of precision, debatable, if I gain what I think is a lot of precision, then I'll go with the reduced model, the simpler model. I mean, the advantage of the simpler model is it's simpler in some sense. But maybe it's not simpler enough for me to think I'm gaining that much from it. So some people have the approach, don't change anything unless you really gain something from dropping a variable. And if you don't gain much precision, don't drop it. That's the other approach. Okay, so that's the process. Now, there's all sorts of things. Now, I gotta see about the time here. Okay, so let me ask you a couple of things about this. Now, suppose instead of three variables, I had 10 variables. I had 10 C's. Not 3, I had 10. And I want to use the all possible subsets approach. Does that bother you? Well, it's a lot more models to consider, right? All possible subsets. All 10, 9, 8, 7, all that stuff, okay? And the table gets bigger, okay? So that's what bothers you, I think. But that doesn't mean you can't do that, because the computer's doing most of the work anyhow. Even if you decide all possible subsets, the computer's the one that's cranking out all these coefficients and stuff and giving you e to the betas and all of that. So you could still have a lot more, bigger table, but you can still get the computer to do that. So that's, you could still argue the all possible subsets approach is correct or is okay or reasonable. Certainly it's reasonable because it considers all possible ways to do things, okay? Now there's two ways I can go on this thing at this point. I can talk about another approach. Okay, let's talk about another approach to assessing confounding. See, the other thing I have to worry about here is, this is a model where there was no interaction. You remember, we found there was no interaction. So we assessed confounding when there was no interaction. So then we have another issue to deal with. What if there's interaction? How do you assess confounding if there's interaction? So that's another thing we got to talk about. I mean, one issue is, what if you had a huge number of variables you're controlling for and there's no interaction? How do you assess confounding? Well, you can still do all possible subsets. Are there any other shortcuts? Okay, that's one way to do it. But a completely different question is what if there's interaction, even if you don't have that many variables, only have 3 variables. So let me talk about one of these and not the other. I'm going to just do one of them. One of the things about what if you have a whole bunch of variables. So suppose you had 10 variables, Not 3, 10. And you didn't want to do the all possible subsets approach. Want to do something different to not to do all possible. What could you do? Well, one of the things I even suggested you could do that isn't right exactly is to do backward significance testing. You had 10 variables, 10 C's. You drop C's that aren't significant until you can't drop any more. So you have an E and you have some subset of the C's. Okay? You get what I just said? You do backward significance testing. What's wrong with that? Already talked about that. What's wrong with whether it's 3 or 10? What's wrong with that? You're doing significance testing to consider confounders. Okay? Okay, so that's not exactly right. But suppose you do this process. You drop, there's 10 C's. You drop 7 of them, say, and you're down with only 3 of them. So you've got E and 3 C's, and you've dropped 7 of them. Okay, so you've got a model, and let's assume there's no interactions, because I'm right now assuming there's no interaction. What's the formula for the odds ratio for the model that just has the 3 C's and the E? E to the beta. Right? There's no interaction. It's still e to the beta. Okay? Now, what if that e to the beta for that model that had only 3, didn't have all 10, is essentially within 10% of the gold standard model that had all 10? What does that mean? That means even though you got to those 3 by doing significance testing, which wasn't exactly right, once you got there, that model that you got controlled for confounding because it gave you an e to the beta that was the same as the gold standard. So you didn't do all possible subsets. You dropped them you dropped 7. You only did 7 steps. You didn't do 35 or 45 models. You looked at 7 different models. Okay? So that's another approach. Okay? That's another approach you could use. Okay? Now, there's problems with that approach. One problem is, what if you got back down to 3? You couldn't drop any more after you got down to 3. And you went e to the beta for that model that had the 3. And you found that e to the beta for that model was meaningfully different, more than 10%, than the gold standard that had 10. What does that mean? Then when you got down to 3, that model won't work. It doesn't control for confounding. If e to the beta in the model that had only 3, by doing this backward elimination significance testing to get to that point. But if that e to the beta is different from the e to the beta for the gold standard, you can't do that. What would you do next? Would you just say, well, I'll just quit, I'll just do all possible subsets, or I'll become a taxi driver or something, I'll just do all possible subsets. Well, what other thing could you do? Think about it. What you could do is you could say, well, look, I dropped them one at a time. I dropped 7 of them to get 3. What was the last one I dropped? I don't know which one it was, but maybe what I should do is add the last one I dropped back in. So now instead of having 3, I have 4. I don't have 10, I have 4. Add the last one that dropped, which was the one that stayed in the longest, add that back in, and look at e to the beta in that model that had 4 C variables, not 3 C variables. And if that e to the beta was the same as the gold standard, what about that? Then I'm good. Then I have a model. I didn't do all possible subsets. I wound up with a model that I couldn't use, but then I changed it a little bit, and I got a model that I could use. Okay, so, and that particular approach, this backward significance testing approach, is sort of a way to assess confounding. Now, where does confidence intervals come in? Did I do any confidence intervals when I described that? I didn't describe, I just did significance testing. Now think about what happens when you do significance testing. When you do significance testing, what are you doing? You're asking whether you're doing a test that, if it's a wall test, you're taking an estimate and dividing by a standard error. And if the standard error is really large, it's not significant. If the standard error is small, it's significant. So if you think about standard errors and confidence intervals, standard errors go into confidence. If the standard error is large, is the confidence interval going to be big or small? Or if the standard error is large, does that mean you have a lot of precision or a little bit of precision? the larger the standard error. The larger the standard error, you have less precision. So if you're talking about the width of a confidence interval, the larger the standard error, the wider or the smaller the confidence interval? The wider. So in some sense, when you're doing this significance testing, you're sort of in a different sort of way without looking at confidence intervals, you're sort of looking at confidence intervals. So you could argue that this backward approach with significance testing, once you then say, well, once I get down to my final thing and I try to add something back if it doesn't work when I'm sort of doing confidence interval evaluation or precision thing as I get down to that model, and then I'm adding something back. And so the model that I finally get, if I add one variable back, is a model that controls for confounding and more or less helps precision because I got to that point by dropping some variables that weren't significant and they weren't contributing a lot to the confidence interval that I might compute for that. So that's what I'm saying. So that's one approach. But there's another approach that I won't talk about until next time. But now what I want to do is, because of time, I want to talk about one other approach. Did you follow that approach? In other words, there's the all possible subsets approach, right? And that's great. That's the best approach. But if you got a lot of subsets, there are some ways around it, and one of which I just described, doing significance testing. But you got to worry about once you do that. It's not you better make sure you assess confounding after you finally get a model that you think is good as far as significance testing. You better assess confounding. Look at e to the beta. Now here's the next thing I want to do. I'm going to just start this. I'm skipping some stuff. Okay. I want to talk about what if interaction. I want to spend about 5 minutes on this. 7 minutes on this. What if interaction? Or we stay until 7. No. What if interaction? Okay. So, find this slide. I've skipped slides. Okay? Because I want to get to this point. We've talked about what if no interaction, and now we're talking about what if interaction. So here's the model that we started off with, right? It had the MRSA model. It had these 3 C's as V's and W's. Okay. Now, what I'm saying is, it didn't happen. It didn't happen. I already went through the interaction assessment. Interaction was not significant. Okay, so I didn't need any of these product terms. But let's sort of hypothesize that maybe it was significant. Maybe something was significant when I did interaction. So let's look what I say here. Suppose the model after interaction was this. See this? Bottom of the screen. Bottom of that slide. See the bottom of that model? What does that mean? Does that mean I found interaction? Yeah, because there's a product term, E times W1. W1 is age. So there's a variable in the model that's in there as a product term with exposure. So there is interaction. I'm saying suppose that's what happened. It didn't happen in this data. Suppose the data set was a little bit different and this happened. Okay. What would I do? Where am I at this point? Do I say, I'm done, this is it, this is the final model? Well, let's put it this way. You remember that hierarchy principle that I talked about if you find something significant, you can't drop some lower order terms? What does this mean? W1 is what? Age. If this is the model after interaction, what can I drop? Well, I certainly can't drop this if this is the interaction, and I can't drop E because that's my exposure variable. What also can I drop? V1 because that's age. But what might I be able to drop? V2 or V3, right? Depending upon whether the odds ratio meaningfully changes when one or more of them are dropped. That's how you have to assess confounding. But now, things are more complicated. Why are they more complicated? What's the formula for the odds ratio for this model? Is it just e to the beta? Is it e to the beta? In this model, if there's this interaction, the formula for the effect of exposure, it's not e to the beta. It's e to the beta plus something. Plus what? Delta 1 times W1, where W1 is age. That's the formula. So let's see if I can find it there. Well, let's see. Okay, let's Here it is. That's the formula for it. Skipped another slide. That's the formula for it. And that's the model we're dealing with. It has E age. I've made it a little simple by writing in the variables. E times age. That's the formula for it. Okay? So, how do we so there's only two variables now. We can't drop age. Age has got to stay in. It's an effect modifier. But maybe we can drop gender or PAMU. And maybe the odds ratio doesn't change. Okay? So, suppose we drop, well, let's put it this way. Suppose we don't drop any of them. We don't drop either. We just keep the model as it is. Okay? How are we going to get the odds ratio? What's the formula for what does this formula say? That the odds ratio is not a single number. It depends upon age, right? I get a different odds ratio depending upon what the age is. So if I wanted to see, even for the gold standard model, what the odds ratio is, I'd have to plug in different age values. If age is a continuous variable, or even if it wasn't, if it was binary, I'd have to plug in two values. But if age is continuous, I get a range of age values, and I get a whole bunch of odds ratios, even for the gold standard model. See what I'm saying? For the gold standard, I get a whole range of odds ratios. And you see where I said tables of odds ratios? For the gold standard model, I'd get a table of odds ratios for all the different ages that I wanted to consider, because age is an effect modifier, and the odds ratio varies with age. Okay? Now, suppose I wanted to drop both of those variables. I wanted to drop gender and PAMU. This would still be if I drop these two, gender and PAMU, what's the formula for the odds ratio? Still the formula. If I drop gender and PAMU, the formula is still e to the beta plus delta 1 times age. Except that beta hat and delta 1 hat might change because I've dropped two variables. I don't know if you get that. You have to think about that. But I've dropped these two variables. Okay? So the issue is it's more complicated. I have to deal with a table. Now, here's an example of a table. Okay? This is just for the gold standard model, for example. I choose 5 values of age. Age is the effect modifier, and I'm going to choose 5 values, whatever I think is right. I mean, I could do it any one of a number of ways. But then, because this is the formula, I get the odds ratio for each of these values of these 5 ages. And I get 5 odds ratios. That's for the gold standard model. So what if I want to see what happens if I drop either V2 or V3 or both of them or neither of them? Well, neither of them is the gold standard model. But what if I drop any one of them? What I'd have to do is I'd have to use the same formula to get a table of odds ratios. Now, here's an example. This is just made up data here, because everything's now made up now because there was no interaction. But now, suppose it turns out, now, I don't know if you can follow me. This is where we're going to, I'm just going to go through this, and then we're going to end today, and then I'll start with this on Thursday. But see if you follow me here. Okay. You got a table of odds ratios. For the gold standard model, suppose for these 5 choices of age, these were the odds ratios. These were the 5 odds ratios for these 5 choices. E to the beta, using e to the beta plus delta 1 age. When I plug in these different age values, I get these 5 different numbers. Suppose I only have V2 in the model. Suppose I have these 5 numbers. Look at these 5 numbers and look at these 5 numbers. What do I have to do to assess confounding here? Confounding. What do I have to do? I have to ask, it's a more complicated question. Is this table, when I drop V3, V2 is the only one in the model, meaningfully different from this table? I'm not just saying, is the 5.4 different from the 5.2? When I take all of this together, is all of this together meaningfully different from all of this together? Well, that's not an easier decision as looking at a 10% rule when I only have one thing to compare. It's more subjective. But if I look at these numbers, I chose these numbers carefully so that, these numbers, these two tables aren't that much different, right? You see that they're not that much different? They're not the same, but they're not that much different. Look at the next table when I drop V2 and I keep V3. Look at this one. Why did I have a no here and a yes here? Why did I have a no here and a yes here? Well, look at this one, 9.2, 5.2, 6.2, 9.0. This table of odds ratios for the gold standard is very meaningfully different taken together from this table of odds ratios. So I don't want to just use this table. I don't want to drop V2. I can drop V3 and I'm okay. What about dropping both of them? Well, look at this, 8.8 to 5.2, 5.9 to 9. I made up these numbers. But what does this say? If you look at this information, if this was your information, what does this say about which subsets of the goal? Now, you only have two variables you're worried about. Should you control for, should you use the gold standard? Can you drop one of the variables? And if you can, which one can you drop? Can you drop both variables? Can you drop both variables? The answer is no. Can you drop this one? No, but you can drop this one. And I'm basically saying if I drop V3, I get the same answer as the gold standard. So these two models, which drops V3 or uses the gold standard, but now has age as an effect modifier, they both control for confounding on the other variables. Okay? So I'm down to two models, just like I was before, but now I'm dealing with interaction. I don't know if you follow me, because, I'm doing this fast here, I guess you might say. Okay, so I'm down to two models. What would I do next? And then I'll repeat this next time. What would I do next? I'm now down to either this model or this model gives me the right answer, because they both control for confounding. How do I choose between them? What's the other word I want to hear? Precision, right? Precision. So what do I have to do? I have to get confidence intervals for each of these two models. Just these two. I don't do it for these two because these two models aren't any good. So I wound up getting confidence intervals, and I'm just showing you. Look at this is the last thing, and I'll repeat this. Look at these two confidence intervals, these two sets of confidence. These are the confidence interval ratios for the two models, the gold standard model and the one that contains gen but dropped the V3. Are they close? Are they close? Well, which one is better? Which one has better precision? This one or this one? CI ratios. The one at the bottom, right? These are all smaller, right? Each one of them, well, this one isn't. It's a little higher, but basically the same. Every other one is smaller. So if it looks like you gain precision by dropping that other variable, PAMU, and you already know that you're dealing with confounding when you drop PAMU. So this model looks better. Now, did you gain meaningful precision when you did this? Well, that's what's debatable. If you decide this is meaningful, like this is meaningful, then you might say, I better go with this second model. So it's the same idea is what I'm saying. If there's interaction, you do the same thing. You assess confounding, you assess precision to decide what the best model is, but it's more complicated because now you have tables of odds ratios to deal with, not a single odds ratio. You have tables because the formula for the odds ratio is more complicated. Done for today, okay? So I'll go over that again, okay? But now I'm just curious. Raise your hand if you feel totally lost about what I just did in the last 10 minutes. Just curious. Totally lost. How about partway, halfway lost? Okay. How about not lost at all? I don't know what that means, but I'll talk about it some more.